All right, welcome back to Physics 221, Chapter 40, One-Dimensional Quantum Mechanics. So we've talked a lot about you use the Schrodinger equation to derive the wave function. And we did that mathematically. It's a lot of work. Well, now what we're going to talk about is wave function shapes. In other words, how to intelligently guess the shape of a wave function. And you can go pretty far, you'll see. But just remember, and I said this at the very beginning of this chapter, Schrodinger, when he came up with his wave equation, he wanted to make sure that the wavelength of the wave function was equal to the de Broglie wavelength, which is h over p, which is h over mv. Okay, so here we go. All right, so consider a particle, a good old particle in a rigid box, right? A one-dimensional rigid box. Now just think of classical physics for a minute. Where is the particle more likely to be found? Where it's going really slowly or really, really fast? So if you want to find, so where do you think? I think you have to you'll answer, hopefully, it's more likely to find it when it's going slowly, right? Because it's spending more time at a particular region. All right. So basically what we're saying is if a particle has small kinetic energy, if it's moving slowly, we expect the amplitude of the wave function to be large. Because remember, the amplitude of the wave function, when you square that, you get the probability of finding the particle. Okay, so that's fact number one. So large wave amplitude means small kinetic energy. Small wave amplitude means large kinetic energy. Okay, here's another kind of hint that's going to help us guess the wave function. So let's think of a bound state wave function as a de Broglie standing wave. And we've done this before. All right? So here's the de Broglie wavelength. I changed it a little bit. So lambda is h over p, which is h over mv, which is h over 2mk square root of. Let me prove that. So kinetic energy is 1/2 mv squared. So if we multiply this by a 2, then we get rid of the half. We multiply it by m. Then we have to multiply this by m. Then if we take a square root, we get mv, which equals p. So all I'm saying is that square root of 2mk is equal to mv, which is equal to p. All right, so let me go back. Okay, so again, we're thinking of a bound state wave function as a de Broglie standing wave, which we've talked about in the past. Now, when the kinetic energy is small, what do we expect the wavelength to be? Well, large, right? Large, because kinetic energy in the denominator. Right? So here's our second fact that's going to help us guess the shape of a wave function. If we have a large amplitude, we have small kinetic energy. If we have small wavelength, we have large kinetic energy. And it just comes from that formula up there. All right, so we have those hints or facts that will help us guess the wave function shape. Now, what else do we know? We know that the number of antinodes is the energy level, right? N equals 4. 1, 2, 3, 4. 1, 2, 3 for E3. Right, we know that. We know also that the depth of the potential energy well has to do with the penetration to the classical forbidden region, right? So here, the potential energy goes to infinity, so there's no penetration into the classically forbidden region. But here, because this is the infinite well, but here's a finite well, right? Finite well, and there's this there's this penetration into the classical forbidden region, okay? So basically, if we have an infinite well, no penetration to the classically forbidden region. If we have a finite well, we know we're going to penetrate the classically forbidden region. So we know a lot, right? Okay, so here's a question for you. So we have 3 de Broglie waves are shown for particles of equal mass. That's important, equal mass. Rank in order from largest to smallest the speeds of particles A, B, and C. And, you know, obviously, you're going to use that. So pause your video and figure it out. All right, so lambda equals h over square root of 2mk. Well, h is the same, 2 is the same, m is the same. So we can say that lambda is proportional to 1 over the square root of k. Well, k is 1/2 mv squared, and all we're really looking at is the v, so we can say that lambda is proportional to 1 over v. Right? All right, so which way? So let's see, what can you say? So these wavelengths, you know, that's pretty much the same, right? So these wavelengths are the same. This is the longest wavelength. So if you have a long, if this is big, what does v have to be? What does it have to be? Come on. All right, okay. So if we have a long wavelength, this is really long, this is big. What? Oh gosh, hold on a second. No. All right. Yeah. Oh, this is good. Okay. So if this is a large wavelength, like we have for C, that means that the speed has to be what? Small. And these are equal. So it does make sense, right? It does make sense. All right. So again, here is everything that we know how to figure out the shape of a wave function. So now I'm going to draw something, and what I'd like you to do, everybody, is, like I always say, pause as soon as I tell you. So pause, and then we'll work on it. So I'm going to draw this on the board. Okay, so this is the graph of u of x. This goes to infinity, that goes to infinity. This is 0. So this is x, right? This is the x. That's L over 2, and that's L. All right, so this is the potential energy, this thing. Sorry. All right, this is just x, but this is really what we concentrate on, the potential energy. Yeah. Okay. Now, let's go back to what we know. Oh, and I forgot E5. That's kind of crucial, right? Okay, so we're given the potential energy, and we know it's the n equals 4. So what I want you to do is look at everything here and draw this on your own and draw the wave function. So draw the wave function right here. All right? So students, pause your video and figure it out. All right, let's talk about it. Okay, so let's see. This is the potential, this is the potential energy. This is the total energy. So as we've talked about many times, this here is the kinetic energy. All right, so here, the kinetic energy is small compared to here and here. Okay. If you have small kinetic energy, number one, large wave amplitude. Well, first of all, I mean, let's do this. It's E5, right? So we're going to have 5 antinodes. So, you know, just drop. cheat sheet always beat, right? All right. Now we're going to adjust this, don't worry. Okay, so 1, 2, 3, 4, 5. Okay, we got the 5 antinodes. Now, small kinetic energy means large wave amplitude. All right, so we want this to be up here, right? Big wave amplitude. Also, large wavelength, small kinetic energy. So we want this wavelength to be bigger. So we got to adjust that too. Let's kind of have it like this. There. Okay, now what else? All right, so let's see. Small kinetic energy is right here, large amplitude. Got it. Small kinetic energy, large wavelength. That is supposed to be large wavelength, right? Okay, got it. Number of antinodes, energy level, 1, 2, 3, 4, 5. Got it. Okay, depth of potential energy well penetration. So this goes to infinity. So you notice there's no penetration, right? There's no penetration into the classically forbidden region. Okay, so there it is. Now, is this the only answer? No. I mean, you could have flipped it. I mean, there's other answers, but all I'm saying is we've covered it, right? Everything there we've covered. All right, so that's the easy one. Now let's do the hard one. So here's the hard one. All right, so hold it. So this, all right, so here, you know, we were given the potential energy function, and we drew the wave function. Now we're going to do the opposite, which is hard, you know. So here's the wave function. What we want to draw is the corresponding energy diagram. So let me copy this first on the board, and you do the same, you know, on a piece of paper. Let's see. Go back to drawing school, man. Good enough. Yeah, I can see. 1, 2, 3. Yeah, I mean, it's not exactly the same, but yeah, not so bad. All right, so draw this on your piece of paper, look at that, and figure out the energy diagram. So there you go. So pause your video and figure it out. Okay, let's talk about this. All right, first of all, 1, 2, 3, 4, 5. So we know we're at E5. Okay, we also know that at the left, see how that looks like it's penetrating into a classically forbidden region, right? I mean, it doesn't just stop like this. It's more like one of these, right? But on the other hand, this one just stops, correct? So this looks like infinite U. This looks like, or how about infinite well? This looks like finite well. Oh, that's weird, right? So we're going to have this part is finite well, this part is infinite well. Oh boy, that's weird. Okay, now here's large amplitude, right? Here's large amplitude. And that means, what does that mean? Small kinetic energy, so slow, right? Small KE. And then the amplitude gets smaller and smaller. If the amplitude gets smaller and smaller, that means that kinetic energy is increasing. So KE, kinetic energy, is increasing that way. All right, let's see. The wavelength, I don't know if I drew the wavelength right. Okay, the wavelength is supposed to get smaller, right? So the wavelength is getting smaller and smaller. So that agrees with this, right? Okay, so I think, let's see, I think we've pretty much covered everything, right? Okay, all right, so let's do it. Okay, so on the right, okay, on the right we have an infinite well, Agree? Infinite well. And then, here's our x, as always. And so this goes to infinity. So this is u equals infinity. This is our x-axis, like always. But then on the left, we have a finite well. Oh, okay. We also have E5, right? So E5. Now, the kinetic energy is increasing. Wow. And finite well. Well, how about something like this? So this is U, right? So this here represents U. So that's U as a function of x. So this is the kinetic energy, right? Kinetic energy. And I'll just do this, make it super clear, right? All right, so, we're going to have, this is the infinite well, this is the finite well. So we're going to have this type of wave function. Kinetic energy starts out really, really small, gets bigger, 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 which is what we have. Okay, so there you go. All right. All right. Right near the beginning, we talked about the fact that when you solve the Schrodinger equation, the most important thing is the potential energy. So, and then we went over different types of potential energy, the U, right? And we went over this example. Well, we discussed this example. This was the hydrogen bromide, right? So this has a mass 80 times that. And it's a molecule, right? And so there's molecular bonds. And how do we always model molecular bonds? With a spring. And so this was our model. We said that this hydrogen atom, is connected by a spring to this big fat stationary bromine, And the potential energy of a spring is 1/2 kx squared. So, so we call this a quantum harmonic oscillator, right? Because this is a spring, it oscillates, right? This oscillates. Okay, so we're not going to do the math because it's pretty challenging. And so I'm just going to give you the results. Okay? So, oh yeah, I'm just reminding you of this. So this is the classic harmonic oscillator. And remember, here, the potential energy equals the total energy, which means the kinetic energy is 0. Same for this. So classically, this is forbidden. Classically, this is forbidden because you can't have negative kinetic energy, right? And so classically, the thing just goes, just oscillates, right? This is just along the x, right? Just oscillates, right? Okay. Classically forbidden, classical turning point, classically forbidden. But this is quantum mechanics. We can do funny things. Okay, so you put in this potential energy function into the Schrodinger equation and you solve it. These are the solutions. So you notice I put the exponentials in yellow. Why did I do that? What do these exponentials mean? Well, they mean that the wave function penetrates into the forbidden region, right? The classically forbidden region, I should say. All right, so we kind of expected that, Also, look, the energy is quantized. And we expected that as well. So that's really nothing new. Now, who cares? Well, all right, so one more picture, then I'll talk about why we care. Okay, so again, this is the potential energy. And for the E1, this is the classical turning point. But voila, what do we see? We see that the wave function, psi1, goes into this classically forbidden region. The same, here's the turning point for E2. And psi goes over there, E3 over there. Okay, so we see the quantized energy, and we see this penetration into the classically forbidden region. All right, now who cares? Why do we care? Well, believe it or not, okay, so let's talk about quantum harmonic oscillator absorption spectroscopy. Believe it or not, this was on the MCAT a few years ago. So that should get your interest if you're going to apply to medical school. So let's see, what's absorption spectroscopy? Well, wait a second, what's spectroscopy? Remember a long time ago, we talked about light passing through a prism, and then light passing through a cloud, and then a prism. Then we were just looking at the light emitted from a cloud, and we saw the spectral lines and all that, and we used the Bohr model to explain that. Okay, so now, that was with atoms. Remember the energy levels and the photons being absorbed and emitted? Well, now we're talking about molecules. And it turns out there's something very similar. It's called absorption spectroscopy. So we have a molecule, you know, let's say it has two atoms, and it's bound by a molecular bond, which we model as a spring, like always, you know. Okay, we want to see what the potential energy diagram looks like. So here it is. So this is a potential energy diagram. Okay. You see allowed energy levels, you know, same old, right? But look, this is the important thing. Look at the bottom. Look at the bottom here. Isn't that pretty similar to a parabola? Well, yeah. And what's a parabola? You know, this is potential energy, right? So isn't this a parabola? Isn't that the classical, I mean, isn't that the harmonic oscillator? That's the thing we just talked about, right? That's the potential energy function for the quantum harmonic oscillator. Whoa! So the lower part of the potential well is nearly a parabola. Now, if that's the case, then we can just, you know, we're just going to say, hey, for this molecule with the two atoms, we're just going to use the results of the quantum harmonic oscillator, right? So in other words, we're going to say, oh, you weren't supposed to see that. Okay, we're just going to use these results. Yeah, these results, or these results. In other words, we're going to use this too. All right, we're going to say that the energy is quantized, and here's the formula. Right. So there you go. So because the bottom of the well is a parabola, we're going to use all of these results. So En equals n minus 1/2 h bar omega. So quantized energy, the whole bit. You know, that's why I did this example. Okay. All right. Now, and again, these are two molecules, right? I mean, two atoms bound together by a spring. And so, you know, what are these energy levels? What are these energy levels? They're just vibrational energy levels. You just imagine these molecules vibrating. And so these are the energies, these vibrational energies. Okay, now typically at room temperatures, you know, atoms and molecules are in their ground state, you know, n equals 1, right? We know that. So how do they go from energy 1 to energy 2? Well, they have to absorb energy from a photon. That's one way to do it, right? They absorb energy from a photon. And it turns out that the energy from here to here is usually infrared. So it's infrared light, right? Infrared light has the energy, just the right energy if this molecule absorbs an infrared photon, it'll have the right energy to hit it, so it goes from energy 1 to energy 2. In other words, this molecule will absorb an infrared photon. All right? Awesome. Now, so what? Well, basically, you know, what did we learn about atomic spectroscopy? Hydrogen, for example, only absorbed photons of certain energies, remember? And therefore, you know, you could look at the absorption graph or the emission graph and figure out what element is what, because you could just measure the wavelength and then figure out the corresponding energy for the energy levels differences. It's the same thing here. It's exactly the same thing here. What you do, I mean, So what we're saying is that every molecule has a unique absorption spectrum. So what you do, you just shine infrared light at different molecules. You'll see where the absorption is, and you have this huge database, of all the absorption spectra of all the different molecules. And so if you need to identify a molecule, you just shine the infrared light at it, see where the absorption peaks are, and then compare it to the knowledge that you have in your database, and bingo, you're done. All right? So it's exactly the same. I mean, it's very, very similar to atomic spectroscopy. Okay. Now what we want to do is we want to look at tunneling a little bit more detail, believe it or not. So, by the way, tunneling, that's the term that's used when the wave function goes into the classically forbidden region. Okay, so classical physics. So here's a hill, potential energy UG, or height, whatever. Okay, the ball has kinetic energy, right? And so in order for the ball to get up here, what has to be true about the kinetic energy? Well, the kinetic energy has to be greater than UG, right? Okay, but that makes sense. All right, now what if the kinetic energy is less than this? Well, then it doesn't get over the hill. What are you going to say, right? I mean, it just doesn't get over the hill. All right, so that's classical physics, but we know in quantum mechanics, we've already learned, right, that this restriction doesn't hold, right? There's penetration into the classical forbidden region. So that means classically this could happen, right? I mean, quantum mechanically this could happen because we've seen it. Okay, so we want to talk about it in gory detail. All right, so here we have here's this, here is the energy of the particle. Here is what we call this potential energy here, right? Potential energy here. And we know that quantum mechanically that the wave function will penetrate into this forbidden region, right? Okay, so let's do it. So psi, okay, the particle approaches from the left with energy E less than U. So classically, sorry guy, you can't get over there, but it does happen. So psi decays exponentially in the classically forbidden region. Now here's what's kind of cool. The particle emerges with the same de Broglie wavelength after tunneling through the energy barrier. So we're going to call this an energy barrier, okay? And again, look at this. The particle emerges with the same de Broglie wavelength after tunneling through the energy barrier. Now, what does that mean? That means that the kinetic energy or the speed doesn't change, right? That's what it means. Now that's weird, right? I mean, think about it. It's hard to think in terms of quantum mechanics, but like if this were like a little termite, going through an energy barrier, you'd think it would lose some energy, right? Well, it doesn't happen. With this wave function, okay, the amplitude is less. We'll get into that, but I mean, the wavelength doesn't change. So the energy here is the same as the energy there. That's weird. Okay, now let's keep going. Okay, we want to just look at this region here. So let's blow it up. All right, there we go. Okay, and again, this is the wave function, right? Now, what we want to do is we want to calculate the probability that the particle is going to go through the barrier. Okay? That's what we're going to do. So here we go. So a while ago in this chapter we had psi of x equals psi edge e to the minus x minus L all over eta. Remember when we were talking about eta? So that's what we had. Now, we're going to make it simple, right? I mean, you know, when we talked about this last time, we said that this was the length, you know, so this was L. But come on, we're only looking at from here to here, you know, so let's just be lazy. Let's call this 0, and we'll call that W. Why not? So now we're going to have that this is psi edge e to the minus x over eta. That's kind of nicer, don't you think? Why not? Furthermore, you know, we want to compare, we want to get a probability. So we want to compare the psi squared here to psi squared there. So let's just call the wave function right here a left. Call the wave function right here a right. Why not? Okay, so we're just going to do this. A left. I mean, whatever. Okay? All right, now, the probability that the thing that it, okay, I'm going to use the word now, tunnels, right? The probability that the particle tunnels through the wave function, through the barrier. So the probability of tunneling, is equal to the wave function here. So psi at x equals w, x equals w squared divided by the wave function here. X equals 0 squared. All right, we can do that. All right, so the wave function at w, we just say a L e to the minus w over eta, but we got to square it, squared, and then we put 0 in here, so we're going to have a L e to the 0 is 1, so we just have AL squared. Well, that's nice, so the AL squareds kill. We just got e to the minus 2 width over eta. All right, that wasn't too hard. Okay. All right, so that's the probability that the particle tunnels. I just did that. All right, and don't forget, so this was our equation of eta, for eta, remember all that? We had that before? Okay. All right, so the probability is an exponential. And you know enough math by now. I mean, exponentials are super dependent on the parameters, right? On the width and on the eta. And of course, the eta depends on the energies and things like that. So this is super, super, super sensitive to the parameters. So here, let me kind of demonstrate that. Okay, so let's just, I'm just making up some stuff, all right? Typical examples. Let's say we have an electron. So this is going to be the mass of an electron. And let's say that the barrier width is a nanometer. Okay, so this is a nanometer. And you'll see why I'm doing this in a few minutes. And then let's say there's not a whole lot of difference in the energy, right? Okay, there's not much difference in the energy. Well, then the probability of tunneling is 3.9%. Well, you know, that's easily measurable. It happens, right? You know, 4%, of course it's going to happen. And we'll see a real-life example in a few minutes. Okay, let's... Now look at how sensitive this probability is to these parameters. Electron, but now we're going to make it 3 times as wide, so 3 nanometers. We're going to keep that the same, right? The difference in energies. But look, we went from basically 4% to 0.006%. That's a huge difference, right? Huge difference. I mean, it's still going to happen, just not very often, you know? Okay, now watch. We'll do a proton. Now, a proton is a big Mack truck compared to a little tiny electron, right? And so a proton, still the same width, 1 is first time, same energy difference, 0.1, and look at the probability, 10 to the minus 64. Well, forget that, right? That's basically 0, you know? So this really happens primarily with electrons. But again, I just wanted to show you, I just wanted to put some numbers in just to show you how sensitive this exponential is, you know, to the various, you know, masses and so forth and so on. Okay. All right, now, do we actually use this tunneling thing? I mean, this completely ridiculous, non-classical characteristic, right? That the wave function penetrates these energy barriers. Completely ridiculous, classically. Do we actually use this? Well, yeah, we do. So let's talk about some applications. Okay, everybody stare at this for a while, and hopefully you'll see 3 letters. See the 3 letters? So I, B, M. So this was done by the scientists at IBM, all right? So in an example of atomic engineering, 35 xenon atoms have been manipulated into position with the probe tip of a scanning electron tunneling microscope. So that's what we're going to talk about just a little bit. A scanning electron tunneling microscope. But I have some cool pictures that were also done with a electron microscope. So this is called carbon monoxide man, carbon monoxide on platinum. All right, anybody know kanji? So according to this, the title is atom, all right? So they iron on copper. So what I read about this is that the literal translation is original child. If anybody knows better, let me know and I'll change my notes. Here's another one. National Institute for Standards and Technology, NIST. All right. So what's going on here? So this is called an electron microscope. All right, so here you go. Are you ready? All right. So basically, you use these things called electron microscopes to make these incredible, to move atoms around and to make super awesome, to take awesome photographs with tons better resolution than anything else that we know of. Okay, so here's a sample, a piece of material. The sample can be modeled as positive ion cores in an electron sea. Okay, so the electrons can move around, you know, and you have these positive ions that are kind of stuck. All right, like in a metal or something like that. Now, these electrons, the electrons are bound to the sample, right? And in order to eject the electrons, they need an energy greater than their work function. You remember work function? Photoelectric effect? Okay, so basically what we have is, okay, so, all right, so in order to eject the electrons, you have to overcome the work function. Great. Now, let's keep reading. Oh, no, okay, so here's an air gap, right? Like a half a nanometer. So this is like this. It's the air gap is the potential barrier, All right. Now look, the potential. All right. So the potential barrier is like 4 electron volts, give or take. Okay. And there's no way a classical electron is going to have enough energy to jump over that air gap. All right? There's no way. I mean, let's put it this way. Well, yeah, let me just say that, okay? There's no way that the electron can do that classically, unless, unless it absorbs a high energy photon or something like that. But we're not doing that. We're not talking about that. We're not doing the photoelectric effect, all right? We're not shining light on it, okay? So how is the electron going to do it? How is the electron going to get above that? Well, so tunneling, okay? So look, all right, so this is a probe, okay? And if the electrons here tunnel, then there'll be a current, agree? See here? So if the electron will go from here to here, that's a movement of charge. and so this will measure the current. All right, so the current is monitored as the probe is moved back and forth across the sample. And the image shows the current as a function of position of the probe tip, giving a profile of the surface. Okay? So basically all I'm saying is that when the electrons tunnel, the current is established, and then the software is able to actually make an image of the surface. So, I mean, I don't want to get into the details, but all I want to say is that this thing, this scanning, tunneling electron microscope, works because these electrons tunnel across this air gap. And there's no way in classical physics that they should be able to do that. But in fact, they do it! And that's why these things work, okay? So all I'm trying to say is that the electron microscope is an example of this quantum mechanical tunneling. That's all I want to say. Here's another example. It's called a tunnel diode, okay? A tunnel diode, or Izaki diode, is a type of semiconductor diode which is capable of very fast operation, well into the microwave frequency region, by using quantum mechanical effects. It was invented in August 1957 by Leo Izaki when he was with the Tokyo, whatever that is, now known as Sony. In 1973, Izaki received the Nobel Prize in Physics for discovering the electron tunneling effect used in these diodes. So diodes are these little tiny things that are used to convert AC power to DC power. They're used in surge protectors and all sorts of different things, all right? Logic gates, radiation detectors, these things are used everywhere. And they work by tunneling. So completely impossible classically, but in fact they work. So by the way, the next chapter is chapter 42, nuclear physics. We're doing chapter 42 before chapter 41. And that's because of lab. We want to do a nuclear physics lab, and that's chapter 42. Okay, so here we're going to learn about this next chapter. So how much detail am I going to go? All right, so why do stars shine? So you have a big giant cloud of gas. Because of gravity, it contracts. As it contracts, it gets hotter and hotter and hotter, conservation of energy, you know. When it gets to a certain temperature, like millions of degrees, a process called fusion begins. When you have fusion, for the first time, you start having outward going forces that basically counteract the gravitational contraction. So the star finally is stable. All right, so this is fusion. This is one form of fusion. So you have these 4 protons. They're fusing together. They're so hot and they're moving so quickly they can fuse, because, you know, they repel. Well, they fuse together. When they fuse together, 2 of the protons become neutrons, and you get gamma ray with light and all this other stuff. We don't worry about it. Now, this relies on tunneling. And we'll see that next chapter, okay? No tunneling, no stars shining, no fusion, we wouldn't be here, okay? All right, well, here's a question for you. A particle with energy E approaches an energy barrier with height U greater than E. So classically, nothing's going to happen, but this is quantum mechanics. If U0, the height, is slowly decreased, the probability that the particle reflects from the barrier does what? So pause your video and figure it out. All right, I hope you understand that as U0 is decreasing, that means the probability of tunneling is increasing. That means the probability of reflection is decreasing. That's all. All right. So here, let's just review now. So chapter 40, one-dimensional quantum mechanics. We introduce a Schrödinger equation as a law of quantum mechanics. We recognize that solutions of the Schrödinger equation give the allowed energies and wave functions and for physical situations that modeled by a potential energy function U. We interpreted wave functions and energy levels, and we talked about tunneling. So real quick, this is the baby version of the Schrödinger equation. One-dimensional, non-relativistic, no time dependence, right? But it was bad enough. And again, think about it. you know, classical mechanics is based on forces. Quantum mechanics is based on energies. Yeah, so, you know, you just multiply this out and you get this. And this is the crucial thing, because every situation has a unique potential energy. So that's the whole point. You've got to figure out the potential energy before you can even solve this equation. And again, this is the kinetic energy. Good golly, what a disaster, right? Using the Schrödinger equation, we can model atomic level situations with potential energy functions. We then solve the Schrödinger equation to find the allowed energies and the corresponding wave functions. And this is all a lot of work, right? Solving the Schrödinger equation. You have to use all the boundary conditions and the whole bit. We can then determine the probability of locating the particle at various locations. You can use the wave function to figure out the kinetic energy, all sorts of things. Anything you want to know about a particle, you use the wave function. Yeah, so all the boundary conditions. Wave functions have to be continuous because of this. Wave functions have to be zero where it can't be found. This sort of makes sense. Because the probability density is wave function squared. They have to be zero at plus or minus infinity because you're not going to be there. And you always got to normalize the wave function. So the probability is 1. You don't want the probability to be 2. What would that mean, you know? It doesn't make any sense. All right, this was the infinite well, right? Quantized energy, no penetration, you know. We learn how to do that. We normalize it to get this. Then we did the finite well. In the shocker here was the tunneling, right? That it's possible to go into the classically forbidden region. But again, we saw, you know, quantized energy. And we talked about how to figure out the shape of a wave function just by using some things that we've learned along the way. And then we talked about this MCAT problem that they had a couple of years ago. The quantum harmonic oscillator. So this is very massive. This is tiny, held together with a spring. That's the molecular bond. Use that, right? That's the harmonic oscillator, potential energy. And then you get these wave functions which have tunneling and quantized energy. And then we applied it to a molecule with 2 atoms. And we said, hey, this is the harmonic oscillator, you know? And again, you use that to figure out which molecules you have. And then we talked about tunneling again. We were able to figure out the probability of tunneling, right there. There it is, right? And this is the answer, and it's incredibly sensitive to the width and to the mass and to the difference of energies. It's incredibly sensitive. And then we saw that, by golly, people actually use this, you know, electron microscopes, diodes, all sorts of things. That's it. Thank you very much.